Hi everyone, this is pre-class video on module 4 on unsymmetrical fault. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE SJBIT. In the second session, I will be explaining how to find the sequence network and fault current for double line to ground fault. In the previous session 1, I explained the unsymmetrical fault analysis introduction and finding the fault current and sequence network for LG and line to line fault. So let us consider the double line to ground fault happens on the unloaded synchronous generator. Here I written the equivalent circuit of three-phase generator. This three-phase generator is under balance condition at the time of fault, and whatever the one phase parameters, the same is there in the other two phases. Example, EAZ is there in the phase B. Here we have EBZ and ECZ, and neutral is grounded through reactance. Because it is a generator, the currents are going out of the winding IA, IB, IC. Here the fault is considered on lines B and C, terminals B and C. These B and C are shorted and it is grounded. That is double line to ground fault. So first we will understand what are the terminal conditions of this. Terminal conditions for this. So since the generator is unloaded, therefore the IA value will be 0, and IB and IC, if you apply the KCL, that is equal to IB plus IC, that is IB and IC when you add, that is the fault current. That will be the fault current. And see here the B and C phase, they are connected in parallel, therefore VB is equal to VC, and it is grounded, therefore this value will be 0 if you consider the directly shorted. Suppose if you are considered the fault through fault impedance, then that value will be ZF into IB plus IC. For this case, let us consider fault without fault impedance. So this is what IA is equal to 0 and IB and IC are zeros if it is directly shorted, and symmetrical component of voltages are given by, that is Vs is equal to 1 by third, that is of the matrix. So this is tau Ps inverse into Vp. Vp is nothing but Va, Vb and Vc. Here Vb and Vc are zeros, Va it is taken as it is. So next I will consider the voltages. So if you expand this matrix, Va naught is equal to 1/3 of Va, and Va1 and Va2 they are equal to 0. So that is Va by 3. So this, if you expand the previous matrix, we will get Va naught is equal to Va divided by 3, and it is equal to Va1 and is equal to Va2. And also it is to know that the IA can be written in terms of symmetrical components, IA naught plus IA1 plus IA2, and this value is 0. So from the sequence networks of the generator, it can be written as Va naught, Va1, Va2, that is equal to Va 0 0 minus Z1 0 0 0, Z2 0 0 0, Z0. So this can be written as VA0 is equal to EA into the currents IA0, IA1 and IA2. This is the matrix equation. It is written for symmetrical components of voltages. So EA minus Z1 IA1, this is 1 2 0, this is 1 2 0, this is 1 2 0. So similarly VA2, this is VA1, VA2 is equal to minus Z2 into IA2 and VA0 is minus Z0 into IA0. From this you can get the expression for IA0. IA0 is minus VA0 by Z0. Similarly IA1 is EA minus VA1 by Z1 and VA and IA2 is minus VA2 by Z2. After this, so we can add the previous here. IA0 is nothing but IA1 plus IA2 plus IA0. We have the expression for IA1, IA0 and IA2. Here you add and equate it to 0. So you will get minus VA0 Z0 minus VA2 Z2 plus EA minus VA1 by Z1 is equal to 0. So if you simplify this further and get the expression for so here VA0 in the previous slide, as you see, VA0 we have formula for VA0, VA2 and VA0, VA1, VA2, VA0. You can substitute here for VA0, VA1, VA2. So you will get the reduced expression, that is minus EA minus IA1 Z1 by Z0 minus EA minus IA1 Z1 by Z2 plus EA minus IA1 Z1 by Z1, that is equal to 0. So here if you simplify the equation for IA1, we will get IA1 is equal to EA upon Z1 plus Z0 plus Z2 plus Z0 plus Z2. So from the derivation we come to know that here the three sequence networks are connected in parallel because current is adding. If the three sequence networks connected in series, current will be equal, but here it is added, means they are connected in parallel. And also it is clearly shown that VA1 is equal to VA2 and it is equal to VA0. So therefore what it is conclude that the three sequence networks are connected in parallel. Three sequence networks are connected in parallel, that is shown here. So here we have positive sequence network, negative sequence network and the zero sequence network of the generator. So they are suppose if you take the positive sequence network here, so it has source voltage and the positive sequence impedance Z1 and the current coming from out here is I here only it is considered IA1. Similarly, here we have Z2, VA2 and IA2. This is negative sequence component, and here this is zero sequence component. They are all connected in parallel. They are all connected in parallel. So, in the previous derivation, it is clearly told that the IA1 value will be EA divided by Z1 plus Z2 Z0 divided by Z0 plus Z2. So, this we can get from here. Here you can get IA1. Here is IA1. So, these two impedances connected in parallel, this is Z0. So, IA1 is equal to EA divided by Z1 plus the parallel combination of these two, that is Z0 Z2 divided by Z0 plus Z2. Whatever the equation it was derived, the same here we got. And also the fault current IB plus IC is nothing but your fault current, that is equal to 3 times of IA0. This IA0 you can derive this from this branch current formula. So, 3 times of IA0. IA0 is equal to, here the branch current formula, this is the branch current, it is coming opposite, therefore minus IA1 divided by opposite branch Z2 plus sum of the branch impedance Z0 plus Z2. So, Z2 into Z2. So, this is the formula for finding the IA0 value. By knowing the IA0 value, you can find the fault current. So, sequence network, this is the sequence network of a double line to ground fault, and this will be the IA0 expression. After this, let us understand the unsymmetrical faults on power system. So, let us consider single line to ground fault on the power system. See here, I have considered line A, line B, line C, and faults are represented like this. In IA phase fault happens, it is a line to ground line. So, line to ground fault it is considered, and second and third line it is not grounded, just it is hanging, no current flows through the hanging line. So, the condition for this, as we all know, so here the no load is connected to B and C. So, IB and IC value will be same and it is equal to 0, and since VA it is shorted to ground, its value will be 0. Its value will be 0. And it is come to know that IA0 is equal to IA1 is equal to IA2 is equal to IA divided by 3, because IA0 is 1/3 of IA plus IB plus IC is the formula for symmetrical component, zero sequence current, 1/3 of IB and IC 0, this is IA. Similarly, you can get it for IA1 and IA2 expressions. So, and IA1 is nothing but VF divided by Z1 plus Z2 plus Z0. So, this is just like the line to ground fault in the previous session I was derived. So, the same lines you can use to find single line to ground fault. So, how the sequence network? See here, the positive, negative and 0 sequence, they are all connected in series, because IA0 is equal to IA1 is equal to IA2, therefore, they are all connected in series, and positive sequence voltage is VA1, negative sequence voltage is VA2, and 0 sequence voltage is VA0. So, next we will see the line to line fault. see here line to line fault you can mark here. See here whatever it is shown in the figure, it is phase A, phase B and phase C, 3 lines on the transmission line. So here fault is considered between the 2 lines, that is B and C, and if the fault happens, the fault current will be IB and it is equal to minus of IC, and here this line is not loaded, therefore the current IA will be 0. So the terminal conditions are IA is equal to 0 and IF is equal to IB and it is equal to minus IC. And from the previous derivation, it is observed that in this case VA1 is equal to VA2 and IA1 will be equal and opposite to IA2 and IA0 value will be 0 and VA0 value will be 0. Therefore, in the in the sequence network of line to line fault, there will be no zero sequence network, and IA1 value will be V1 divided VF divided by Z1 plus Z2. You can observe this sequence network. So here positive and negative sequence networks, they are connected in parallel. So here the positive sequence network voltage is VA1 and IA1, negative sequence voltage is VA2 and the current is IA2. They are connected in parallel. And next let us see the double line to ground fault. So in the beginning of this session I explained, here we have considered 3 stubs here, 1, 2, 3, and it is considered double line to ground fault. Therefore, a line B and a line C we have considered, here fault happened and it is connected to ground. So here the system is unloaded, therefore no current flows through the line A, and line B and line C it is shorted, therefore IB plus IC will be the fault current, and that will be calculated. And VB and VC will be 0. VB and VC will be 0 because it is shorted to ground. Therefore, and it is observed from the previous derivation that the fault current is IB plus IC and it is equal to 3 times of IA0, and in this derivation it is known in the beginning of the session. So here all the 3 sequence voltages are connected in parallel. Why? Because their voltages are same, and current value will be this. See here the sequence network, positive sequence network, negative sequence network and zero sequence network, since the voltages are same, they are connected in parallel, and the currents coming out of the positive sequence network and negative sequence network and zero sequence network put together will be, suppose if you write KCL at this node, so then IA1 plus IA2 plus IA0 will be equal to 0, that is equal to IA. So in these lines you can understand. Next we will consider the 3-phase fault on a power system. 3-phase fault is nothing but it is a symmetrical fault. Fault current is same in all the 3 lines, and the fault current value is IA is VF divided by ZF. This is just like a positive sequence network. Normal power system analysis, how we do, the same lines we can use to find the fault current for a 3-phase fault. With this I will be ending the video.